Okay, time to get started. Okay, so we're getting started now. Here's what we were talking about last time. So we are getting started now. I need everyone to stop. Okay, all right. So we were talking about vector line integrals, right? And the motivating application that we started with was the idea of computing how much work it takes to move against a force field along a path when that force field might not be constant, when that path might be curved, et cetera, et cetera. So powerful motivating example, but not the only way in which vector line integrals are useful. So we asked the question, well, what if the vector field represents a fluid flow? Now how should I interpret a vector line integral? What does it mean? And we got a kind of I'm going to call it a weird answer. And what I mean by weird is unfamiliar. It's not something that we've talked about previously. It's not something you've probably seen in other contexts, if I had to guess. So here's what it is. It represents the fluid flowing along the curve, to put it as succinctly as possible. So now, specifically, it's a rate per unit area, right? And that's just the way the calculation works out, is what it is. I think that's pretty natural. Obviously, more area cross-section means more fluid, right? So, of course, it should be in some way related to area, and not surprising that it's proportional to area. So factoring that out makes sense, I would argue. And it's a nice punchline. To what extent is the fluid flowing along the curve? So it is, again, not a familiar physical object, physical quantity, but it is something that's naturally meaningful. Okay, so then we wrapped it up by considering this special case, and specifically this special case is about closed curves. Not all curves are closed, of course, right? So vector line integrals are defined in general for any curve. Appropriately regular. Let's not get into the weeds. In that special case, the vector line integral has a name. It's called circulation. And I think it's a pretty plausible name. If you think about it, a closed curve kind of wraps around on itself. The tangent vector, if you look at the unit tangent vector as you go along, that unit tangent vector literally goes around in a circle, right? And so if we're measuring the extent to which the fluid flows along and kind of does what that curve is doing, circulation seems like a reasonable term. Okay. All right. So we talked through a couple of examples of this, and you can sort of see it in action here in this first example, just to kind of remind ourselves. There's the fluid flow. Here's how the curve is going. To what extent is the fluid flowing along the curve? Well, yeah, a lot, right? I mean, it totally is, right? And so hopefully no surprise that in this case, for this vector field and for that curve, the circulation is positive. Does that seem reasonable to everybody? Can everybody kind of see the sort of, what we have arguably a geometric way to visualize over here is going to be measured by this algebraic object here. Okay. All right, and then likewise, of course, if they're going the other way, and let's see here, here we have the fluid is flowing like that, but the curve is going like this. So to what extent is the fluid flowing along the curve? Well, it's kind of the opposite. It's doing the opposite of what the curve is doing. So hopefully a reasonable interpretation then is that this should reflect that it's doing the opposite by giving a negative value. Does that seem reasonable? Okay, good deal. Okay, so picking up from here, this is where we left off. Now, we have a weirder circumstance over here. I mean, what should I imagine about the circulation around this curve here? Well, I mean, on the one hand, kind of on the left side of the curve, if you will, it appears that the fluid is flowing opposite of the direction of the curve. But over here on the right side, of course, the fluid is going to be going consistent with the direction of the curve. So it's like we got a little tug of war, some negative, some positive. Not clear how that's going to work out. And sometimes it is just not immediately obvious at casual glance. In fact, usually it's not immediately obvious at a casual glance. So that's why I call this a question mark. Now, you could probably make a reasonable guess. You know, do you see more positive or more negative here? And you could probably, again, kind of eyeball and make a reasonable guess. But in general, that's hard to do. Okay. And by the way, we will have a much more powerful way to approach this question. Hopefully by the end of today, we'll see how things move along. Okay. All right. Okay, last I want to give you sort of an interpretation. I think this is very helpful. This is going to be helpful both in terms of applications and in terms of how we're going to visualize another important algebraic construction that's going to come up again later today, and that is, how can I imagine what other takes might I try to adopt for how to visualize circulation? So here for whatever it's worth, if you have an object floating in your fluid. All right, so now keep in mind this is a two-dimensional vector field, so I'm imagining this being a two-dimensional fluid, and I've got this object sitting there, floating on top of it. How should I interpret the circulation here? And the idea, and this is just a take, but again, I think really helpful, the circulation, I would propose, tells you something about how the fluid would cause that object to rotate. So in particular, with the fluid doing like this, right, positive circulation, well, what do you think would happen to this object? The fluid is doing what we see in this picture. Is this fluid going to rotate clockwise? No. Right? It's clearly going to be rotating counterclockwise. That's what the fluid is kind of doing to it. Does that make sense? Everybody? So we call that positive because in this case, keep in mind, the curve along which we're interested in the circulation is going that way. So when we compute this circulation, we are saying, hey, by the way, this curve going as it is counterclockwise, we're going to call that the positive direction. And then a positive circulation says it's rotating in what we've agreed is the positive direction because we oriented the curve counterclockwise, and so counterclockwise. On the other hand, now keep in mind, same fluid. Let's see here, colors. Let me think about this object here. And now notice, my curve, though, is going clockwise. So how does that change things? And algebraically, it makes a big difference. Algebraically, it makes your circulation colors. Makes my circulation turn out to be negative. Does that mean the leaf rotates the other direction? Actually, no. It changes the way we've described the question. Our curve, now being oriented clockwise, when we compute that circulation, we're going to get an answer to the question of to what extent is this fluid rotating this leaf floating in the fluid? To what extent is it rotating it clockwise? Because that's the curve we're using. And again, same fluid, same floating leaf. To what extent is that leaf going to be rotating clockwise? Well, quite the opposite, isn't it? It's the same fluid, same leaf. It's still going to be rotating counterclockwise. It's just that now counterclockwise is negative because we've defined clockwise to be positive. Everybody on board with that? Okay, so helpful point of view. It's going to come up again in a few minutes. Okay. So just a few more things we need to say about vector line integrals in general. We do have a formula. You parameterize the curve. You pull back through parameterization, and you can take a deep breath and plow forward, and you can compute that out, and sometimes it can be tedious, right? Capitalize when you have an opportunity to capitalize, and sometimes you get lucky. This is pretty fabulous that this works out sometimes. Here's a nice example. So let's think about this curve C, and here is what I'm going to call a parameterization of it. Now, asterisk. This is not giving x, y, and z as functions of t. Parameterization is supposed to be rectangular coordinates as functions of t. This is giving spherical coordinates as a function of t. So when I call this a parameterization, what I mean is you can solve for x, y, and z. We've got formulas for how to compute x, y, and z. That's the parameterization that's indicated by this. And it's a nightmare of a curve. I mean, if you just look at the formula there, the formula for phi, the formula for theta, this is ugly. We're going to be looking at sines and cosines of these already fairly unappealing expressions. And so this is going to be really, really hard to understand. But I claim that I immediately know that it is entirely contained on the sphere rho equals 1, because check it out, it says so right there. This parameterization, I don't care what t is, rho is always 1. So we are always on the surface of that unit sphere. Is that cool? Here's the other observation to make. You look at this vector field, and okay, all right, man, that's a lot. You keep in mind that what I've got written here is R. That's actually the vector field x comma y comma z. Right? And you could multiply that out, but let's not multiply it out. It's actually to our advantage to realize that vector field, you can see it right here, it is a scalar multiple of the position vector r. Right? So the position vector r, wherever you might happen to be on the sphere, always perpendicular to the sphere. Cool thing about spheres centered at the origin is that the position vector is always perpendicular to the surface. Is that geometrically? Does everybody buy that? Yeah.
But how do you know it's like that curve?
I don't know. The whole point to this squiggle curve that I drew is it's some wacky curve that's on the sphere.
Okay.
So yeah. The specifics I had no idea. Yeah. So, okay, a lot that we don't know. I mean, obviously this scalar multiple you would think matters. And my picture doesn't recognize that. The particulars of the curve you'd think matter, right? But, so I've just drawn some random squiggle. How is this good enough? And I claim that, in fact, we're basically done at this point. Because what we see from all of this, let me just get rid of, I've got too much going on here. What we see from all of this is that our vector field here, F, is always perpendicular to the sphere. But my curve being entirely on the sphere means that my dr vector here, how I move, is always parallel to the sphere. Right? This is fabulous. What that tells me then, this dot product, F dot dr, well, there's F. It's perpendicular to the sphere. There's dr. It's parallel to the sphere. That dot product is a dot product of two perpendicular vectors. That dot product is 0. And that means that integral then also 0. And we didn't have to deal with that nasty parameterization at all. What do you think? So heads up, right? Keep on the lookout. How often does stuff like this come up? Surprisingly often. We, as a rule, when we look at engineering problems or physics problems, we're not looking at random, pointlessly amorphic shapes, right? We're looking typically at shapes that are natural, shapes that come up and for reasonable reasons, right? Engineering is a very organized business in some sense, right? And so very often we're looking at spheres. Very often we're looking at things that are simple. And things that are simple tend to have nice symmetries. And again, this comes up surprisingly often, right? So please do keep a lookout. I would encourage you, when you see a vector line integral, don't just go plugging and chugging just because we have a formula, right? Always kind of take a step back and think, okay, are there any freebies here? What leaps off the page at me is obviously, convenient, and how can I capitalize on that and save myself loads of trouble? Okay. All right. This is mostly notation. As far as we're concerned, this is mostly notation. This is actually, from a deep mathematical point of view, really, really important. But it's really, really important at levels that are beyond what we can reasonably do in this course. So as far as we're concerned, this is just kind of notation. And so, old news. Write this out in coordinates. Yawn. Nothing happened there. Distribute the dt. Whatever. Right? And then it seems pretty natural to name, for example, x prime dt dx. And likewise dy and dz. So the nice punchline is this gives us an alternative notation for our dr vector. What I will call a coordinate notation for our dr vector. So, okay. Let's write that down. And then keeping in mind that our vector field, whatever that is, that's going to have coordinates. And by the way, for right or wrong, good or bad, it's fairly common to write those coordinates as P, Q, and R. It's kind of a strange choice. I don't know why, but this is the fairly common choice. Wouldn't say universal, it's common. So, okay, anyway, P, Q, and R, you write those coordinates out, and now you could just crank out this dot product, right? This dot right there, we know the coordinates of the things that we're dotting, and doesn't it seem reasonable to kind of write it out like that? It's just notation, right? But that kind of seems like a reasonable thing to do. And with that noted, we now have an alternative notation to represent a vector line integral. So, is this a good thing? Do we like this notation? I'm going to say in Math219, I'm going to say not really. Let's think pros and cons. The notation on the left over there is more compact. The notation on the left has the advantage that this is a geometrically natural thing. That's, depending on the context, either a force, that's a physical thing, or it's a flow field, like a velocity, maybe density times velocity, depending on what you're doing. That's something physically natural. What is dr? Well, it's something that's geometrically natural. It represents how I'm displacing along the curve. All this stuff over here on the right, it's a lot harder to make sense out of, at least directly, right? So what is this q, for example? Well, okay, it's the second coordinate of my vector field, fine, but coordinates are kind of arbitrary. Coordinates are always with respect to a basis. Your basis is arbitrary. It's not really what I would call physically natural. Right? So what we have here, case can be made, at least based on what we're doing here, is clunky and unnatural. So what's the selling point? And again, for our purposes, this is mostly liability and not really a win. That said, it turns out that the best way to understand all of this stuff that we're doing, and I'm just going to be able to wave my hands at this. This is deep water. This is sophisticated stuff. This is modern mathematics that I'm about to wave my hands at. I am personally 2 degrees of separation from the guy who came up with this. Right? It's very modern. It turns out that this is basically what we call a differential form. Okay, this is called a differential one form. And differential forms in general are how you make the most mathematically natural, best sense out of vector line integrals and various other kinds of integrals that we're going to talk about in this class. So this is tip of the iceberg of some really powerful, sophisticated stuff that we're not going to do anything with in this course, right? So nothing you need to worry about, but nevertheless, we should have some appropriate respect with that in mind for that notation. And why do you need to care? Well, it's in common use. And so even though we're not going to be able to see why this is a helpful notation or why this is a powerful notation, other people who are aware of that and who do work with that kind of thing will use this notation. So you've got to be prepared for what you're going to do when you see that. Right? And so when you see this notation, what I would encourage you to do is to say, all right, look, these integrands here, the integrand for the dx, the dy, and the dz integral, those are just telling me what the vector field is for what is in fact a vector line integral. And the dx and the dy and the dz, that's just kind of a notational alternative for dr, in other words, indicating to me that this is a vector line. So I would encourage you to, anytime you see one of these, interpret it correspondingly like this. How we doing? Is that all right? I really wish we had time to talk about how great this notation is, what you can do with this, and it's a lot, and just not appropriate for this course. Okay, so here we go. Symmetry theorem. Y'all know I'm a big fan. Symmetry theorem. You will probably notice the way I've written this down on the page. I have deliberately laid it out on the page in exactly the same format as several previous theorems that we've seen about symmetry. Right? So we saw a one-dimensional symmetry theorem, two-dimensional, three-dimensional. All basically the same idea. Right? And so nothing really all that different here. Scalar line integrals totally work. So keep a lookout for the idea that your curve might be symmetric over some line. Or in 3 dimensions, that your curve might be symmetric across some plane. Right? Because if so, take a more careful look at that integrand. And if that integrand is odd over the same line, then you're done. This integral is zero by symmetry. Really, really helpful to be on the lookout for that. Okay, is that cool? Asterisk. Got to be careful about this. This is scalar line integrals only. Scalar line integrals only. For vector line integrals, it does not work. There is no such theorem. Specifically, there is no odd symmetry theorem. There are different little clever games that you can play, and you can make up symmetry theorems that do actually work, but the way I like to say this, you can get yourself into more trouble than you can get yourself out of trying to play with those theorems. So I am deliberately not going to present those theorems. I think it would be counterproductive. But anyway, as far as we're concerned, concerning odd symmetry, vector line integrals doesn't work. And you can see why pretty easily, because here's our vector line integral, and keep in mind this dr right here is just kind of a package that contains both t and ds, and you can argue very reasonably that this ds, well, you know, over here on that side and over here on this side, these ds's, they kind of match up, and you can, so they pair, they're the same size, and you could see where an argument would start to come together. But the problem is these t vectors don't. They're not the same. And it's worse than that. not only are they not the same, they're not negatives of each other either. They're just different, right? And so that throws a massive wrench into the works, and we lose. You're not going to be able to make an odd symmetry theorem work. Does everybody see why we would sort of, in fact, not expect that to work out? Okay, so do be very careful about this, and if you apply a symmetry theorem, make sure that it is only being applied to a scalar line integral. Okay, so that's 6.1. So 6.2, this is where things start to get exciting for me. This is where things are going to start to get intricate and complex, and everything's going to connect in multiple different ways. These are fascinating, exciting ideas that mathematicians wondered about for over 100 years, trying to figure out how to bring together a collection of ideas that for, again, 100 years were suspiciously similar but seemingly disconnected. This is my take on how to think about it, and I think in the long run this will make things seem more natural. I think this is really natural. And so anyway, here we go. Let's just dive in. Oh, and then I should mention, yes, we're in section 6.2, but this thing that I'm about to show you is going to apply to several different huge theorems that we're going to discuss. In some sense, the two biggest theorems in chapter 6, and the arguably 3, maybe 4, depending on how you count, biggest theorems of chapter 7 are all, my humble opinion, best understood from the following point of view. Right? So, our first application will be Green's theorem, but it applies much more broadly. There's the idea. I want to define something called a quantity on areas. This is not a deep idea. All we mean by a quantity on areas is that if you give me a two-dimensional region, right? Two-dimensional, because we're talking about areas. You give me a two-dimensional region, a quantity defined on areas, just gives me a value that I associate to that area. That's it. You give me an area, I give you a value. This is what we're going to call a quantity. Okay, so again, not deep water, but some silly examples. If you give me some region, some two-dimensional region like this, a quantity I can talk about would be, for example, I wanted to change the color. We can talk about how much mass is in that region. That'd be a quantity. Because you give me a region, I can count up and see how much mass is in there. Likewise, we could talk about what the area of that region is. We could talk about what the perimeter of that region is. That's all we mean. Here's where something powerful is going to happen. What do we mean by an accumulating quantity? Now, you've heard me say that phrase a lot, right? And the way I've phrased it is the quantity is an accumulating quantity if the whole is the sum of the parts. If you can chop it up into little pieces and look at each little piece and then add it up. And lots of quantities are accumulating quantities. So, for example, here we have two regions. We got R1 and R2. Now let's talk about mass. If I ask how much mass is in the union, disjoint union, well, that's the amount of mass on the left plus the amount of mass on the right. The whole is the sum of the parts. Right? Likewise area, likewise population of bacteria, whatever. But not perimeter. Right? So I think this is an important counterexample. Not everything is an accumulating quantity. There's plenty of things I might be interested in that I can associate to a region that just don't accumulate. And the reason why, and you sort of, think through the picture, the perimeter of R1 is kind of, if you will, sort of that distance. And the perimeter of R2 is that distance. And the perimeter of the union is that distance. And is green plus blue equal to purple? Why, no, it's not. Green and blue have got some stuff happening here on this sort of shared boundary. Right? Purple doesn't. So, not an accumulating quantity. Yeah.
So would it typically be when the two parts share part of the quantity, and that's when it's not?
I hear what you're saying. Tempting. I'm going to say that's a tempting thought. That's a naturally tempting thought. And the big punchline that we're going to see in 2 pages of lecture notes is that it's actually not true. But I like where your head's at. That's a natural way to think about it. That is what goes wrong here. But it's just not that simple. Yeah. But a big reveal to come in a couple of pages. Okay, so I think this is an important counterexample because we need to recognize not everything accumulates so that we can appreciate and know what to look for and therefore have the ability to capitalize on quantities that do accumulate. Okay. This next thing is just a point of view. It's just a way of thinking about things. I think this is valuable. All accumulating quantities you can think of as being like a physical stuff. It doesn't mean that it is a physical stuff, but it behaves like it's a physical stuff, even if it isn't. So, for example, let's talk about work. Here's a quantity, and so, for example, maybe this is the bottom of a swimming pool that I have to clean. It's been drained already, and I have to get down there with a toothbrush or whatever, and I just got to clean the bottom of the pool. Oh gosh, that's going to be a lot of work, right? Well, work is not a physical stuff, right? It's not concrete stuff. But I can think of it as a stuff. I can pretend that this is a kind of a substance that is spread out over the bottom of the pool, and that when I'm computing the total amount of that substance, that's an accumulating quantity. So surely we'll agree that the work is an accumulating quantity. I mean, the amount of effort that I have to expend to clean that little square plus the amount of effort it takes to clean the next square. The whole is the sum of the parts. Well, of course it is. It isn't a stuff, though, but I can think of it like it's a stuff. Because let's face it, if it were actually a stuff, if my imagination were right, if work actually were a stuff distributed over this region, how would I compute the total amount of whatever that imaginary stuff is? I would chop it up into little pieces, and I would argue that the whole is the sum of the parts, which we just agreed it is. So it's a little con, almost, that we can pull on ourselves to give us a way of visualizing something that, even though it isn't technically true, is going to guide us in the right direction. Okay, so I think this is very helpful. That noted, and again, this is going to seem a little weird, this idea of density, right? Mass per unit size. We've understood density previously as mass per unit size. Mass per unit area, if we're talking about it being distributed over areas. Well, this numerator can be any accumulating quantity. Any accumulating quantity at all. All I need to do really is to be able to associate whatever this accumulating quantity is. I need to be able to associate it to little pieces so that I can talk about how much of that stuff, real or imaginary, is associated to any given little piece so that I can compute the corresponding density. So a little bit weird. Now I know you all have seen the following before, but there is this idea of population density, right? That gets discussed, and when you're looking at how people, where people live, and this kind of thing. And well, population is an accumulating quantity because the whole is the sum of the parts. And then I can therefore talk about that stuff per unit area. Is that cool? Everybody happy? And this one's not that weird because population, it's kind of a stuff, right? We're made out of stuff, right? And again, here's where it gets a little weird. I'm going to talk about work density. Going back to my cleaning the swimming pool analogy. And what do I mean by work density? Well, work is an accumulating quantity. That means I can view it as making sense. For any given little region, we can talk about how much work overall is happening in that little piece that I think of as being a kind of a stuff in that little region. And therefore, I can talk about the associated idea of that stuff per unit area. So work density, a lot harder to kind of wrap your brain around, but makes, I think, a natural expression. How are we doing? Is everybody kind of on board? Okay. All right. By the way, don't forget, we think of densities as stuff per unit area, but another way to say that is that it's what you multiply by area to get stuff. All right. And, well, don't forget what we do with densities. They're integrands. Right? So now again, the most relatable, the most familiar example of this is that if I look at mass and I argue, look, I can compute mass by making an accumulation argument because after all, mass has the feature that it is the sum of the parts. Right? Accumulating quantity. And then I can say, look, I know how much of that there is in any given region because we know the corresponding idea of mass density. So I can turn a dm into density times dA. And well, okay, likewise, if work is an accumulating quantity, right, as we previously discussed, I can talk about how much work there is in a given amount of area, and the integrand, again, then is a density. Now it's work per unit area, so it's work density instead of mass density. It's analogous, morally kind of the same. Everybody happy? All right. All right, so what we have here is a strategy for computation. We identify accumulating quantities. First, we identify quantities as being associated to areas. Then we recognize, fingers crossed, hopefully, that they're accumulating quantities. Once they're accumulating quantities, I know I can compute them with integrals, and the integrand is the associated density. So this is, like I say, a little roadmap, and we're going to make a bunch of arguments that follow this basic roadmap. We're going to identify accumulating quantities. We're going to figure out, some way or another, what the associated density is. That'll be our integrand, and we'll compute with an integral. Okay, so again, 6 or 7, depending on how you count, big theorems are all going to fit this roadmap. Okay. And I like to make the case, I think really all integrals can be thought of this way. Just a little bit of terminology. Sometimes I call these accumulation theorems because the fact that they are accumulating quantities is really kind of the key point. And then also sometimes I like to call these density theorems because the density is the integrand. So that's just terminology, but anyway, you're going to hear me say both of those expressions here and there. Okay. Oh, and then I've drawn the pictures and made the arguments here concerning areas, but you can also talk about stuff accumulating over volumes. Density then being quantity per unit volume. And you can also talk about stuff accumulating over accumulating over lengths. So same basic idea, just sort of dimensionally different. Okay. All right, so that was all abstractions. Now let's apply it to a specific case. We're going to look in 2 dimensions. We're going to see what I'm going to call a very surprising example. This is really hard to see coming. Sneaks up on us. It's going to seem wrong at first. It really is going to seem wrong. And in order to make sense out of this, I do have to develop a little bit of convention before we can get right down to it. We need to talk about boundaries. I think y'all are probably previously familiar with the idea of a boundary. It's where you put the fence. That's what the fence around the boundary is what defines what's inside the fence, and the fence is the boundary of what's inside the fence, right? I mean, it's a pretty familiar idea. Yeah. The new concept here is that we now need to think of boundaries as being oriented things. The word boundary, going forward, means oriented according to a specific convention. We have not thought of boundaries as being oriented up to now. Boundaries were just fences. It's where you put the fence. It's the edge. It's the border between my set and not my set, right? Real simple idea. Going forward, it's an oriented thing. And oriented according to a very specific convention. Here's the convention. If you have some region, like so, the correct orientation, which region is the correct direction along that boundary? The correct direction to go is the direction such that as you go that way, the region whose boundary you're talking about is on the left. Now this is an arbitrary convention. Somebody pulled this out of thin air. Had they chosen a different convention way back when, I suppose it wouldn't have mattered. But the convention is heavily standardized at this point, and so this is what I'm going to call arbitrary, but not optional, right? So this is important. It does have to be this way because this is to be fair, arbitrary, but the convention that planet Earth uses. So again, very important. It's got to be on the left. So notice if this is me walking along maybe this green region is a nice pretty grassy field, and I'm walking along the boundary of that field. As I walk along here, going that way, notice the region is on my left. That makes sense to everybody? And of course, now that you can't say that it'll always be as in this picture here. Okay, that means it's going to the right, but it's not always going to be to the right because over here I would have to go this way in order to have the region on my left. Again, as this is me walking along, go that way to have the region on my left. Everybody all right? Okay, watch out for the standard blunder. Lots of students make this blunder and make the observation based on what we call simply connected regions like this, that, doesn't that mean that we're always going counterclockwise? Because check it out, counterclockwise puts the region on the left. And so a lot of times people mistakenly think that the convention is always go counterclockwise. This is not true. This is a real problem, right? And the easy counterexample is, what if we have a grassy field like this that has a couple of lakes in it? Something like that. All right, and at a point like this, which direction do I go? I picked the wrong color. Sorry. Which direction at a point like this, which direction do I go to put the region onto my left? Well, I would have to go clockwise. Everybody see that? Okay, so don't buy into the oversimplification. Think it through carefully. And by the way, yes, to be fair, if you know for sure that you're going around the outside of whatever your region is, then yeah, sure, counterclockwise, absolutely. Just that's a secondary special case, yes.
Or you just following the direction of the loop your point is on?
Say it one more time.
Aren't you just following the direction of the loop your point is on? Our point is going.
Well, so very importantly, though, I've drawn these arrows to be consistent with the convention. The convention is not to be consistent with the arrows. So the arrows are a consequence of the convention. Does that make sense?
For this one, the one with the lakes in it.
Yeah.
If you're in the smaller lake, you're still going the same direction as the direction of the lake.
Yeah, no, right, absolutely. But my point is that if I have a region like this, and if I were to have drawn my picture differently, if I were to have drawn, let's see, color choices. If I had drawn my arrows like this, and then if I ask what's the boundary of the green region, it's not what I have drawn in red here. The word boundary is strict. The boundary says, I don't care what you thought about the curve, right? What you previously may have thought about the curve is not my problem. You say the word boundary, we have to follow this convention here, right? And so said differently, if I were to call this curve C, and let me give a name to my region. If I call my region D, the boundary of D is not C. The boundary of D is the opposite orientation of C. Does that make sense? Yeah. It's a great question, and this is a subtlety that a lot of students do have a lot of trouble with. So, great question. The word boundary is very specific to this convention, and if you thought you had an orientation on a boundary curve previously, it is you got to eject that and reevaluate. Yeah. Okay, so we're ready. This is at the center. This is the nugget behind our first example of one of the biggest ideas in the course. It's this argument right here. It's a beautiful little argument. I claim that boundary circulation is an accumulating quantity. And this does not seem right. Let me try to make the case for why this seems wrong. This totally seems wrong. Because look, I mean, boundary circulation, to be an accumulating quantity, we need the whole to be the sum of the parts. So look, let's think about D1. And if I'm looking at this region D1, actually, let me do it like this. If I look at this region D1, and if I ask, okay, what is the boundary circulation around D1. Well, I've got to look at this D1. I've got to think about its boundary curve. I've then got to think about a vector line integral going around that boundary. And of course, the vector line integral, the boundary goes this way. The vector line integral, the boundary circulation would be oriented as I have it drawn there. Now let's think about D2. Here's D2. And looking at D2, if I ask what is the boundary circulation, so I got to take D2, I got to imagine, okay, what is the boundary curve for D2? You got to follow those boundary conventions, and that is a line integral along kind of like this. Right? So I've drawn here the boundary circulation for D1. I've drawn the boundary circulation for D2. Now let's look at the whole. The whole is the union. It's this whole great big schmear here, right? And for that region, the boundary circulation, well, I got to go all the way around the entire boundary. Like so. And now let's look at these circulations. Is green plus light blue equal to violet, dark blue, whatever. Is green plus light blue equal to violet? I don't think it doesn't look like it. Right? Look at all this stuff in the middle. It's kind of like that example you were asking about where, the problem is there's kind of a shared boundary curve in the middle. These pieces, right, they have this boundary in the middle that's not part of the boundary of the whole. And it seems like this has failed. And the key point, the thing that makes all of this work is if I erase everything that cancels, like along in here it cancels. Along in here it cancels. If we erase everything that cancels and look at what's left, this is the disparity. This is the problem. Yeah, but that problem is two line integrals over the same curve but with opposite orientations, and they cancel in a puff of smoke. The disparity is zero. There is no disparity. This works. And so boundary circulation is an accumulating quantity. Everybody see that? Super powerful idea. This is underneath kind of all of it. This is what's going to make Green's theorem work for us next time. So we'll pick up here on Wednesday. Y'all have a good rest of your Monday. More on this later. See you later. Thanks for the